Here is the physics question. So I'm working through some practice problems for electric fields and electric potential. In this case, we have an electric dipole. So there's a positive charge Q, negative charge Q, negative Q. They both have a charge of 2 nanocoulombs. So plus 2 nanocoulombs, minus 2 nanocoulombs. And they're separated by a distance 2 millimeters. I just made this problem up. Like I said, I made the problem up. So the question says, if I wanted to bring an electron from infinity to right there, point B, how much energy would that take to do? And then do the same thing for point A. So let's do point B first. Okay, so we're talking about the change in energy to move in an electron. You can't use like the force, because as I bring the force in from infinite distance, the value of the force changes, so I can't really calculate the work. It's not an easy thing to do. However, I can use the work energy principle. Work is the change in energy. So that's what I want to find for my system consisting of these charges and the electron. So that means that I can write the change in energy as the charge. I'll write the charge of electron as Q for right now, which is negative E, but I know, times the change in electric potential. So that means this is going to be Q times V2 minus V1. And that's the energy needed to bring it in. Okay, so right off the bat, if I start with my electron way over here at an infinite distance away, there's no electric potential because it's an infinite distance. And as I move it right here, all I need to do is find the potential right here, V1. Okay, so remember that if I have a point charge, the electric potential due to a point charge is K, Q over R, where Q is the charge and R is the distance. And so I need to find that right here. And it's the potential due to both of these two charges for V1. So V1 is going to be K, Q, I'm going to call this Q plus R plus K, Q minus over R minus. So what's Q minus and Q plus? Well, that's Q plus, that's Q minus. I think that kind of makes sense. What's R plus and R minus? R plus is this distance. So R plus is going to be equal to, well, this is 2 millimeters and this is 5 millimeters. That's 1 millimeter. So this is going to be 6 millimeters. So 6 times 10 to the negative 3 meters. R minus is going to be this distance. So it's going to be 4 millimeters. 4 times 10 to the negative 3 meters. So now I can put in my values and calculate V1, and then I can multiply by the charge of an electron, and I'll be done. Okay, so it's not that bad. Okay, so let's go ahead and put in our values here. Remember that K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. So I'm just going to put everything in to get V1. And then I can calculate delta E. So V1 is going to be, I'm going to factor out the K and the Q just so I don't have to write them twice. So I get 9 times 10 to the 9th. Q is 2 nanocoulombs. So a nano is 10 to the negative 9th. So I get 2 times 10 to the negative 9th. And then I'm running out of room here. I don't always plan very well. So let's plan better. So V1 is going to be 9 times 10 to the 9th, 2 times 10 to the negative 9th. And now I have this, I have plus 1, because I factor out the K, Q, plus 1 over R plus. So it's 1 over 6 times 10 to the negative 3, plus minus 1 over 4 times 10 to the negative 3. Right, because this is a negative charge. I factored out the value of Q. Now over here, we can do a little math trick. If I have 10 to the 9th times 10 to the negative 9th, it's 1. Nice. And then I have 2 times 9 is 18. So this whole thing is just 18. Okay, let's just go ahead and put it in our calculator. You use your calculator as you prefer. I'll use my calculator as I prefer. So drop that. So I get 18, and then I'm going to enter this. So 1 6 times 10 to the negative 3 divided by, and then 1, 4 times 10 to the negative 3 minus, divided by, minus, and then times, and I get V1 negative 1499.999. So let's say negative 1500 volts. Now back up here, my change in energy, I can find that delta E is going to be the charge of an electron, which is negative 1.6 times 10 to the negative 19th, times V2, which was I'm sorry, that's V2. I calculate V1. I'm bringing it in. So this is V2. It's early in the morning. I apologize. Yeah, V2 minus V1. Final minus initial. It's an easy thing. I'm not going to redo the video because if you made this far and you're thinking that guy's so dumb, I get it. And I approve of that. And that's a minus. Wow, it is early. Okay. So, and then multiplied by this. Negative 1500, and I get a change in energy of 1.6 negative 19 times. I get 2.4 times 10 to the negative 16 joules. Okay, what about point A? How much energy would it take to bring the charge from electron in from infinity to point A? And you may think, well, that's really wild, right? Because now I have to go along this weird path like that or something like that. But if you remember, when we define electric potential or potential energy at all, it's path independent. We can take whatever path we want. So it doesn't really matter where I start at an infinite distance. They're all the same. They're all zero. So I could start over here, move over to infinite distance that way, and then come down. But it doesn't matter. All I need to do is to calculate the potential at point A, and then, so I just need to redo the thing and use this point right here. So let's look at the potential at point A. So at point A, I can say I'm just going to call it VA. It's going to be the potential due to this charge, K Q plus over R plus K Q minus over R minus. That's exactly what I had before. But now you'll notice right here that this is R plus. I have to find that distance. And I can do that because I know this length and I know that length. And I know I need to find this distance. I know that length and I know that length. But I'm not going to do that because I can just skip something. It doesn't really matter what those are. If I calculated those distances, they're the same. And potential is a scalar. So it doesn't really matter about the direction. So if I calculate the distance, that distance is the same as that distance. So just call them R. So this is going to be equal to K over R times Q minus Q. Because that's the charge in the positive, that's the charge in the negative, and Q minus Q is 0. So the potential at A is 0. So now I can calculate the change in energy. It's going to be the charge of an electron, which I'm just calling Q, times the final potential, which is 0, minus the initial potential, which is 0, which is 0 joules. So you don't need to bring this in. It doesn't need any work to take it in. And let me show you one really quick reason why. If I have this dipole, and I'm looking at on this axis, the electric field points that way. So as I move it along here, I'm moving in the direction perpendicular to the electric field. So the electric force is perpendicular to the direction of motion, so it requires 0 work. Same as carrying something sideways, horizontal to gravity, required 0 physics work to move that. I dropped my chalk. Okay, so that's a problem.